February 18, 1944. Inside a massive factory in Wichita, Kansas. The metal is too hot to touch with bare hands. The air is thick with oil, burned aluminum, and the sharp sting of ozone. Pneumatic hammers slam again and again, the vibration pressing into the chest like a forced heartbeat. Steady, mechanical, unforgiving. Overhead, long rows of fluorescent lights tremble, their pale glow reflecting off an unfinished aircraft fuselage, its surface scarred by welds that haven't cooled yet. A man stands on scaffolding nearly 10 meters above the factory floor. His gloves are soaked with oil. Sweat darkens his shirt even though winter grips the outside air. He stares into an empty metal cavity where ducts, wiring, and mounting frames should already exist. There is no complete blueprint in his hands. Only a smudged sheet of notes, a few numbers crossed out, and a short order. It must be finished today. A piercing screech cuts through the noise as a sheet of aluminum is forced out of alignment. Pressure spikes inside the compressed air line. Someone shouts at the far end of the assembly line, but the sound is swallowed by the machines. The man freezes for half a second, too long for a system already in motion, then keeps working. If he stops, the entire line behind him will lock up. No one inside this factory fully understands how the machine they are building is supposed to function. But everyone knows one thing. If something goes wrong here, the consequences will not stay inside these walls. This is not a story about a lack of technology. The United States in 1944 had steel, engines, scientists, money, and manpower in abundance. What it lacked was not inside laboratories, but somewhere far more dangerous, time to fully understand what it was building. That is where the paradox lies, a system powerful enough to erect entire factories in months, yet forced to let production run before a complete blueprint even existed. Industry moved ahead of engineering. Manufacturing ran ahead of understanding. Decisions were made while no one could see the whole picture. The machine did not fail because it was weak. It struggled because it was born inside a system that could not afford to stop and think. This is not a question of whether it could be built. The real question is far more unsettling. How much error can a system absorb when the system itself is still being constructed while in motion? Years before that moment, the war had entered a phase where every calculation was distorted by time. Not the time shown on clocks, but logistical time. How many aircraft were lost each month? How many squadrons failed to return? How many weeks remained before the enemy adapted? Reports flowing into Washington did not speak in emotional terms. They spoke in shortages. Gaps in the sky were growing wider, and those gaps had to be filled faster than the enemy could destroy what already existed. Political pressure left no room for delay. Every week of hesitation meant hundreds of missions that could not be flown, targets left untouched, and a war dragged out longer than planned. Yet engineering pressure pointed in the opposite direction. What was being demanded had never been produced at this scale, never assembled at this speed, and never tested under such compressed timelines. There were no perfect options. Only two paths, both dangerous. If nothing was done, the system would have nothing to send to the front. The gaps would widen, and the war would collect its price elsewhere, in blood. If action was taken, it meant building in partial darkness, designs changing midstream, processes reversed, tens of thousands of people working on components they would never see as a whole. Every decision became a gamble, not between right and wrong, but between delay and error. In this environment, risk was no longer a personal choice. It became a command issued by the system itself. The factory was not built to serve a finished design. It was built to serve a number. How many fuselages had to leave the line each month? How many wings had to be mated? How many engines had to be mounted? Once that number was fixed, everything else was forced to adapt. Assembly lines were laid out before engineers finalized the structure. The spacing between stations, the load limits of the floors, the height of the cranes, everything rested on assumptions that were expected to work themselves out later. They rarely did. A minor change in the load-bearing frame made hundreds of jigs unusable overnight. A drill hole misaligned by a few millimeters in the forward fuselage had to be compensated with metal shims farther down the line, adding weight that no calculation had planned for. Each aircraft contained hundreds of thousands of parts produced by hundreds of subcontractors, all working to different tolerances and timelines. When even one shipment arrived late, the line ahead was forced to run blind. Temporary installations, markings instead of final fittings, assemblies built only to be torn apart later. Engineers knew this was inefficient. Workers were never told why they had to install and remove the same components 2 or 3 times in a single shift. Managers looked only at the progress charts. If the line stopped, losses were measured in minutes. The consequences of a design compromise, however, would not appear until thousands of flight hours later. And so the same solution was chosen again and again. Temporary reinforcement, added complexity, extra weight, anything that kept production moving. The factory continued to run, even as no one could say with confidence whether the system was stabilizing or merely accumulating hidden errors. The most serious problems were never the ones that were easy to see. They lived in the layers where systems overlapped. When a design change was issued, information did not travel cleanly down the line. It bent and fractured as it passed through layers of mediation, hand-corrected drawings, condensed telegrams, temporary notes taped to bulletin boards. One shift might still be working from an outdated version, while the next had already moved on. 2 aircraft could look identical on the outside while being structurally different on the inside, and no one at the end of the line had the time to tell them apart. For the workers, the job became purely procedural. Install, tighten, mark, move on. They did not know the altitude the aircraft would fly at, the loads it would endure, or why a fuel line had been rerouted at the last minute into a tighter bend. Test pilots, at the far end of the system, were the first to feel the consequences. Unusual vibrations at high speed. Electrical systems responding too slowly. Minor failures not listed in any manual, but their reports had to travel backward through the same overloaded system, often arriving only after the production line had already advanced to the next batch. Managers understood the risk, but they understood the numbers more clearly. Each day of delay meant dozens of unfinished airframes, hundreds of idle workers, and intensified political pressure. So more patches were applied, additional inspections after assembly, on-site fixes, acceptance of variation between production runs. No one believed this was sustainable. But inside a system driven by the clock, imperfection became the price paid to keep everything in motion. No one inside this factory is allowed to believe they are the center of anything. The system does not revolve around individuals, it revolves around tempo. Workers start their shifts before daylight and leave while the lights inside the plant are still burning. Their bodies adapt to constant noise, to vibrations traveling through steel floors, to the smell of metal and solvents that never fully fades. Fatigue is no longer a condition, it becomes the baseline. Mistakes do not come from carelessness, but from overload. A step missed after 10 hours on one's feet. A bolt tightened by feel, but without a secondary check because the next shift is already waiting. Young engineers, barely out of school, are forced to approve changes they know have not been fully tested. They are aware of it, and that awareness creates a pressure heavier than any direct order. There are individuals who stand out. A foreman struggling to keep the line from collapsing, an engineer revising drawings through the night. But they are not heroes. They are simply people positioned at the intersection of decision and consequence. When a system demands speed, doubt must be compressed and buried. No one has the authority to stop everything. And in that condition, the most human decisions are often made in the most mechanical way. Wow, the cost did not appear the moment an aircraft rolled off the line. It surfaced later, scattered, delayed, and difficult to trace back to a single cause. Accidents during testing increased not because of one obvious fatal flaw, but because of chains of small errors accumulating over time. An electrical system pushed beyond its limits at high altitude. A structural element operating outside its safety margin because of added weight from temporary reinforcements. These incidents did not always end in catastrophe, but each one added another report. Another unanswered question. Money burned quietly. Every unplanned repair hour, every component replaced after installation, every extended test flight expanded the bill. But in wartime, cost was not measured in budgets. It was measured in speed. Time was lost in a different way. Weeks spent correcting problems that would not have existed had the system been allowed to mature more slowly. And above all, there were people. Test pilots flying machines whose risks were not yet fully documented, workers carrying cumulative injuries, both physical and mental, from a tempo that allowed no recovery. There was no single figure that captured this price. It existed as a composite of accidents, exhaustion, waste, and decisions made without full visibility. The system kept moving, not because the cost was calmly accepted, but because within the imposed timeline, there was no alternative. In the end, the system produced what it had been built to deliver. The line reached its intended tempo. Airframes left the factory more consistently, with fewer teardowns, fewer last-minute reversals. Designs slowly stabilized, not because they had been perfected in advance, but because the largest errors had been worn down through experience and loss. There was no sense of triumph attached to this outcome, no moment of celebration inside the plant, only sustained exhaustion and a quiet understanding that the system had survived by enduring its own methods. The aircraft flew, performed their missions, and were eventually replaced by improved versions, shaped by lessons that were never formally recorded as a single chapter. History tends to remember the final result. For those inside the system, that result simply marked the moment when things stopped shaking violently enough to continue. Not ideal, not complete, just sufficient to keep the war from lasting longer. This story did not end with the war. It repeats itself, under more refined forms. In the modern world, technological, military, and industrial systems are still often pushed into operation before they are fully understood. Global supply chains expand faster than the ability to control risk. Software is deployed while still being patched. Factories are built on forecasts, then corrected by reality. Time pressure has not disappeared. It has only changed shape. The lesson is not about condemning risk-taking. In many cases, controlled risk is what pushes societies forward. The problem lies in how systems consistently underestimate the cost of letting industry run ahead of engineering. Small errors, hidden by speed and scale, accumulate until they can no longer be ignored. And when they surface, the price is rarely paid in spreadsheets alone. It is paid by people and by long-term stability. What stands out is not whether they succeeded or failed, but how they chose to operate while unfinished. That choice was systemic, and that same choice continues to shape the modern world, where there is not always time to wait for perfection. History is not decided by the moment a trigger is pulled or metal collides in the sky, but by the silent systems behind it, where people are forced to solve unsolved problems while the clock keeps running. Long before the first battle begins, the outcome has already been set in motion.